There are objects in the universe that do not merely challenge our understanding, they force it to break. For decades, physicists have searched for a place in nature where the deepest laws of reality collide, a place where space-time and information can no longer be treated separately. Astrophysicist Brian Cox has described black holes as the only objects we know that demand such a confrontation not in thought experiments, but in the real universe. Not because they are mysterious, but because they are unavoidable. Black holes did not enter physics as exotic discoveries or cosmic curiosities. They emerged as mathematical consequences of gravity itself, consequences that many hoped nature would never allow to exist. They arise when gravity is no longer treated as a force but as the geometry of reality. When space can curve, time can slow and collapse, has no mechanism left to stop it. And once black holes appear in the equations, something deeply uncomfortable becomes impossible to ignore. General relativity and quantum mechanics, the two most successful theories in the history of physics, both claim authority over these regions. Both are experimentally verified. Both are mathematically precise. Yet inside a black hole they give mutually incompatible answers. This is why black holes are not simply extreme stars. They are stress tests for reality itself. For much of the 20th century, many physicists believed nature would somehow avoid this contradiction, that collapse would halt, that singularities would never fully form, that black holes were mathematical artifacts rather than physical entities. Nature did not cooperate. Today we observe black holes at the centers of galaxies. We detect their collisions through ripples in spacetime itself. They are not rare. They are not exceptional. They are structural elements of the cosmos, and that realization changes the question entirely. If black holes exist, then the universe contains regions where space behaves strangely. Time loses its familiar meaning and information itself appears threatened. Regions where our most trusted laws do not fail but reveal their limits. This video does not treat black holes as cosmic monsters. Instead, it examines them as the pressure points of physics, the places where the universe exposes the seams beneath reality. To understand black holes is not simply to understand gravity or collapsed stars. It is to confront questions far more fundamental. What is space? What is time? And what happens when the universe refuses to obey the rules we once believed were absolute? Long before black holes became objects we could point telescopes toward, they existed only as an uncomfortable possibility. Not in the sky, but in the logic of gravity. In the late 18th century, long before space and time were woven together, gravity was understood as a simple pull. Mass attracted mass, and every object, no matter how heavy, could in principle be escaped if you moved fast enough. This idea led to a quiet but unsettling question. What if an object became so massive that even light could not escape its gravitational pull? At the time, this was not a question about space-time or horizons. It was a question about speed, about escape velocity. If gravity grew stronger as mass increased, then perhaps there existed stars so heavy that light itself would fail to get away. These hypothetical objects were sometimes called dark stars, not because they bent reality, but because they hid behind their own gravity. Yet in this early picture, something crucial was missing. Mass alone was not the key. The true breakthrough came much later when gravity was no longer treated as a force acting across space, but as the shape of space itself. When Einstein introduced general relativity, gravity became geometry. Space could curve, time could slow, and mass no longer simply attracted, it reshaped the stage on which reality unfolded. Within this framework, an entirely new kind of darkness emerged. It was no longer necessary to imagine stars of unimaginable mass. Instead, any object could become a black hole if it were compressed enough. Even Earth, if crushed to a sphere smaller than a marble, would trap light forever. This was not a problem of material strength. It was a problem of space-time. And here physics hesitated. The equations allowed such objects, but many physicists doubted nature would permit them. They seemed too extreme, too paradoxical, too destructive to the structure of physical law. Singularities appeared, places where density became infinite and equations lost meaning. These were not just technical problems, they felt like warning signs. For decades, black holes were treated as mathematical curiosities, interesting solutions, dangerous ideas, useful for exploring equations but unlikely to exist in the real universe. The prevailing belief was simple: nature would find a way out, collapse would stop, something would intervene, reality would remain well behaved. But the universe was under no obligation to respect human intuition. As calculations improved, it became clear that under the right conditions, collapse had no escape route. No known force could halt it. Not pressure, not radiation, not nuclear reactions. Once a massive star exhausted its fuel, gravity would win. And when it did, the equations no longer described a star. They described something far more radical, something that would force physics to confront itself. There is a point in physics where resistance no longer matters. For most of a star's life, gravity is held in check. Nuclear reactions in its core push outward, balancing the immense weight of its own mass. Light itself becomes a structural support pressing back against collapse. But this balance is temporary. When a massive star exhausts its fuel, the outward pressure fades. Gravity, patient and relentless, takes over. And once it does, the question is no longer whether collapse will occur, but whether anything can stop it. Early on, physicists hoped the answer might be yes. Perhaps matter would become incompressible. Perhaps quantum effects would intervene. Perhaps nature had built-in safeguards against total collapse. One by one, those hopes failed. Calculations revealed a grim simplicity. Above a certain mass, no known force can halt gravity's advance. Not electromagnetic repulsion, not nuclear pressure, not quantum mechanics as it was understood. Collapse does not slow, it does not hesitate, it accelerates. As matter falls inward, space-time itself responds. Time begins to distort. Paths that once led outward curve back in. What had been an ordinary star becomes something qualitatively different. This is the moment a black hole is born. Not in an explosion, not in a flash of light, but in silence. From the outside, collapse appears to freeze. The star seems to dim, then fade, its surface slowing as it approaches a boundary it never quite crosses. Time stretches, signals weaken. The process appears unfinished. But this is an illusion of perspective. From within, collapse completes itself. Matter passes through a point of no return. There is no dramatic threshold, no physical wall, only a region beyond which escape is no longer part of the universe's geometry. This boundary is not defined by force, it is defined by fate. Once crossed, every possible future leads inward. This realization shattered a long-standing belief in physics, that nature would always protect itself from extremes, that infinities were signs of incomplete mathematics, not physical reality. Black holes showed otherwise. They are not accidents. They are not rare. They are the natural outcome of gravity given enough mass and time, and with that realization a deeper problem emerged. Because if black holes are real and collapse truly completes, then the universe contains regions where information disappears from view, where time behaves asymmetrically, and where classical intuition breaks down completely. Gravity had won. But in doing so, it exposed a far greater conflict, one that would soon force physicists to confront the limits of reality itself. The most dangerous feature of a black hole is not hidden at its center, it lies at its edge. This boundary is known as the event horizon, a surface in space that marks the point of no return. Cross it and no signal, no particle, no future path can ever lead back out. At least that is how it is often described. But this description hides a deeper problem. The event horizon is not a physical surface. There is no wall, no membrane, no sudden change in temperature or pressure. Nothing marks the moment of crossing, at least not for the one who falls in. And yet from the outside, something extraordinary appears to happen. As an object approaches the horizon, its motion slows. Light redshifts. Signals take longer to escape. Time itself seems to stretch and thin until at the boundary it appears to stop altogether. To an external observer, the falling object never quite crosses the horizon. It freezes. This prediction unsettled physicists for decades. If time truly stopped at the horizon, how could collapse ever complete? How could a black hole fully form? Was the horizon a real boundary or a mathematical illusion? The resolution lies in one of the most counterintuitive truths of relativity. Time does not behave the same way for all observers. What appears frozen from one perspective proceeds normally from another. For the infalling observer, clocks tick as usual. Space feels ordinary. The horizon is crossed without drama, without warning. Two descriptions of reality coexist. Both are correct. Neither can be privileged as absolute. This was not merely a technical subtlety. It forced physicists to abandon a deeply ingrained intuition that there exists a single universal flow of time shared by all observers. The event horizon exposed time as a relational quantity dependent on motion, gravity, and position in space-time. But even once this confusion was resolved, the horizon refused to become benign, because it raised a far more troubling question. If information falls toward the horizon and appears frozen, then never quite entering the black hole from the outside perspective, then where is that information truly located? Is it inside? Is it spread across the horizon? Or is the question itself meaningless? The event horizon is not just a boundary of escape. It is a boundary of description, and beyond it the language of classical physics begins to falter, not because it is wrong, but because it is no longer sufficient. What lay ahead was not a problem at the center of the black hole. It was a problem at the horizon itself. For decades, black holes were thought to be perfectly silent. From the outside, they swallowed matter and light without leaving a trace. Nothing escaped. Nothing returned. They were cosmic endpoints where the story of falling matter simply ended. Then quantum mechanics entered the horizon. When physicists began examining what happens at the edge of a black hole using quantum theory, they encountered something profoundly unsettling. Empty space, according to quantum mechanics, is never truly empty. Even in the darkest vacuum, particles flicker in and out of existence, appearing briefly before annihilating one another. This restless activity occurs everywhere in the universe. But near a black hole, the rules change. At the event horizon, these fleeting quantum fluctuations can be torn apart. One particle may fall inward, forever trapped. The other may escape outward, becoming real, not virtual, carrying energy away from the black hole itself. The consequence is unavoidable. Black holes emit radiation, not as jets, not as light beams, but as a faint, steady glow born from the quantum nature of space. This radiation is unimaginably weak for large black holes invisible to any telescope we can build today. And yet its existence changes everything, because emission means loss. As radiation escapes, the black hole loses mass. As mass decreases, gravity weakens. Over immense spans of time, the black hole shrinks. Eventually, given enough time, it disappears entirely. Black holes are not eternal, they die. This realization shattered a long-held picture of the universe. Objects once believed to be perfect prisons turned out to be temporary. Collapse did not lead to permanent erasure. The universe, it seemed, always finds a way to give something back. But this apparent reassurance came with a far deeper cost. Because if black holes evaporate completely, then everything that ever fell into them must confront a final question. Not a question of energy, not a question of matter, but a question of information. If a black hole forms from a star swallows, planets, absorbs light, and then vanishes into a cloud of faint radiation, does the universe remember what was lost? Or has something fundamental been erased? What began as a subtle quantum correction at the edge of a black hole had now evolved into one of the most serious crises in theoretical physics, and it would soon be known by a single unsettling name. In physics, destruction is never complete. Burn a book, shatter a planet, reduce a star to radiation. In principle, the universe keeps track. Every interaction preserves information about what came before, not as memory in the human sense, but as correlations embedded in particles, fields, and waves. This principle lies at the heart of quantum mechanics. It is not optional. It is structural. Nothing is ever truly erased, and yet black holes appear to do exactly that. If matter falls into a black hole, classical relativity offers a simple answer. It crosses the horizon and continues toward a singularity, a region where known laws of physics no longer apply. From there, no signal can return. Quantum mechanics complicates the picture. As black holes radiate and slowly evaporate, all that remains in the far future is a cloud of thermal radiation, featureless, random, carrying no obvious imprint of the star, planet, or particle that once fell in. If that description is correct, then something extraordinary has occurred. Information has been destroyed. Not hidden, not scrambled, gone. This possibility struck at the foundations of physics. If black holes erase information, then the universe itself is fundamentally non-deterministic in a way quantum theory forbids. Cause and effect would fracture. Predictability would fail at the deepest level. The conflict was not philosophical. It was mathematical. Two frameworks, both trusted, both tested, made mutually exclusive claims about reality. One had to give. For years, physicists debated which law should be sacrificed. Some argued that quantum mechanics might be incomplete. Others suggested that black holes represented a new category of exception, a place where information conservation simply does not apply. But this was an uncomfortable compromise, because black holes are not rare anomalies. They form naturally, they persist, they interact with the universe at large. Allowing them to destroy information would mean rewriting the rules everywhere. Gradually, a different possibility gained traction. Perhaps information is not destroyed, but hidden in a way classical intuition cannot grasp. Perhaps it does not disappear into the singularity, but becomes encoded in subtle correlations within the radiation itself, not readable in practice, but preserved in principle. If true, this would mean that black holes do not violate quantum mechanics. Instead, they demand a radical rethinking of how information is stored, transported, and revealed by spacetime. The paradox would not be resolved by abandoning a law of physics. It would be resolved by discovering that space and time are not what they appear to be. To resolve the information paradox, physics was forced into an unfamiliar position. It could no longer treat space and time as the unquestioned backdrop of reality. Because if information truly survives the life and death of a black hole, then it cannot simply fall into a region where space ends and time terminates. It must be stored somehow within the structure of the universe itself. This led to a startling reversal. Instead of asking how information moves through space and time, physicists began asking whether space and time themselves are built from information. In everyday experience, space feels fundamental. It is where things exist. Time feels fundamental. It is what allows events to unfold. Physics had always assumed both as given. Black holes challenged that assumption. Calculations revealed something deeply counterintuitive. The amount of information a black hole can contain is not proportional to its volume, but to the area of its boundary, the event horizon. This was not a small technical detail. It suggested that the universe does not store information the way we expect. A region of space behaves as though its contents are encoded on its surface, not within its interior. Reality, it seemed, was holographic. In a hologram, a two-dimensional surface contains all the information needed to produce a three-dimensional image. Remove part of the surface and the image degrades, but it does not disappear entirely. Information is distributed, redundant, resilient. Black holes appear to operate on a similar principle. If information about everything that falls in is preserved, then it may not reside deep inside the black hole at all. It may be encoded at the boundary in correlations too subtle to detect directly but exact in principle. This reframed the problem completely. The event horizon was no longer just a boundary of escape. It became a boundary of description, and space itself began to look less like a stage and more like a consequence. According to emerging ideas, space-time is not the fundamental fabric of reality. It is an emergent structure arising from deeper quantum relationships, much as temperature emerges from the motion of atoms or pressure emerges from countless collisions. You do not find temperature by zooming in far enough. You find atoms. Likewise, you may not find spacetime by zooming in on spacetime. You may find something else entirely. Entanglement, correlation, information. In this view, distance is not primary. Time is not absolute. Geometry itself is secondary. What we experience as space and time may be the large-scale manifestation of an underlying quantum system that does not resemble space at all. Black holes did not merely hint at this possibility, they forced it. By demanding that information survive where space appears to fail, they compelled physics to abandon its most comfortable assumptions and replace them with something stranger, deeper, and still unfinished. And yet this was only the beginning, because if space-time emerges from information, then the universe itself may be far more computational than anyone ever expected. Once physicists began treating information as fundamental, an unexpected parallel emerged. Not from astronomy, not from cosmology, but from computation. In modern physics, information is not abstract. It is physical. It must be stored, transmitted, and protected against noise. And nowhere is this challenge more severe than in quantum systems. Quantum information is fragile. Interact with the environment in the slightest way and it degrades. Errors appear instantly. Coherence is lost. For decades, this fragility was considered a fatal obstacle to building practical quantum computers. Then something remarkable happened. These strategies developed to protect quantum information, known as quantum error correction, began to resemble the strategies nature itself appears to use in black holes. In these systems, information is not stored in one location. It is distributed redundantly across many degrees of freedom. Lose part of the system and the information does not vanish. It remains recoverable, at least in principle. This is precisely the kind of robustness black holes seem to exhibit. If information that falls into a black hole is preserved, then it cannot be localized. It must be spread across the horizon in a way that resists destruction even as the black hole evaporates. This reframes the horizon yet again. It is no longer a surface where physics fails. It is a surface where information is encoded with extraordinary efficiency. In some theoretical models, spacetime itself behaves like a quantum error correcting code. Geometry emerges from patterns of entanglement. Distances correspond to correlations. Connectivity arises from information flow. This is not metaphor. In simplified mathematical settings, these ideas can be made precise. Remove too much information and spacetime tears apart. Preserve enough structure and geometry remains intact. The implications are profound. It suggests that the universe is not merely governed by laws that resemble computation. It may be built from computational principles at the deepest level. Spacetime is stable not because it is rigid, but because it is redundantly encoded. Reality persists not because it is indestructible, but because it is error-tolerant. Black holes, once thought to be destroyers of information, may instead be its most sophisticated guardians. They force information to spread. They forbid localization. They demand protection. And in doing so, they hint at a universe whose deepest structure is not made of space-time or matter, but of relationships that can be counted, corrected, and conserved. Yet this realization carries a further consequence. If space-time itself is emergent and computational, then black holes are not just exotic objects within the universe. They are probes revealing how the universe is assembled, and that makes their presence everywhere not incidental but essential. For a long time, black holes were treated as theoretical curiosities useful for testing ideas but distant from observation. That separation no longer exists. Today, black holes announce their presence across the universe, not through light but through influence. They shape galaxies, stir matter, and send vibrations through space-time itself. At the hearts of most galaxies lies a colossal presence, a supermassive black hole millions or billions of times more massive than the Sun, anchoring the motion of stars and gas around it. These objects are not passive occupants. Their growth and activity appear tightly linked to the evolution of their host galaxies. As matter spirals inward, enormous energy is released. Jets carve through interstellar space. Radiation regulates star formations. Entire galactic ecosystems respond to the behavior of something smaller than the solar system. This is not coincidence. It suggests that black holes are not mere byproducts of cosmic evolution. They are participants, perhaps even organizers. And then there is collision. When black holes merge, they do not collide like solid objects. They coalesce. Their horizons distort, their geometries interlock, and the universe responds by ringing like a struck bell. These rings travel outward as gravitational waves ripples in space-time itself. By detecting them, humanity has gained a new sense. We can now listen to the universe, not just look at it. And what we hear are black holes again and again announcing their existence through the fabric of reality. These observations confirm something essential. Black holes are not rare anomalies hidden in mathematical corners. They are common. They are dynamic. They are woven into the large-scale structure of the cosmos, and this ubiquity sharpens the stakes of the theoretical questions. If black holes truly preserve information, if space-time emerges from deeper principles, then these are not esoteric concerns confined to extreme edges. They are relevant everywhere. Because galaxies formed in the early universe. Because black holes appeared early. Because the rules they reveal may have shaped cosmic history from the beginning. Understanding black holes is no longer optional. It is a prerequisite for understanding how the universe became what it is. And once that realization sets in, the scope of the story expands yet again. Because a universe structured by black holes is also a universe defined by vast distances, immense timescales, and a haunting silence. A silence that raises a different kind of question, not about gravity, not about information, but about life. A universe shaped by black holes is not a quiet one. It is violent, dynamic, and crowded with matter and energy. Galaxies collide. Stars are born and die. Gravity sculpts structure on every scale we can observe. And yet when we listen for something else, for signals, for intentions, for intelligence, we hear nothing. This contrast is unsettling. Hundreds of billions of stars populate a typical galaxy. Most are now known to host planets. Across the observable universe, there may be trillions of galaxies each with countless worlds. Time too is abundant. The cosmos has existed for billions of years, more than enough for complexity to arise. By any naive accounting, the universe should be alive with activity. But it is not. This tension lies at the heart of what is often called the cosmic silence. A discrepancy between expectation and observation so stark that it resists easy explanation. The question is not whether life could exist elsewhere. The question is why, if it does, we see no trace of it. One possibility is rarity. That the chain of events required to transform chemistry into biology, biology into intelligence, and intelligence into technology, is far more fragile than it appears from our singular example. Another is instability, that even when intelligence arises, it seldom lasts long enough to leave a lasting mark. Civilizations may emerge, peak, and disappear on timescales too short to overlap. There are also darker possibilities, that the universe selects against visibility, that advanced societies learn to remain quiet, hidden, or inward-looking, or that the same technologies that enable expansion also enable self-destruction. None of these explanations can yet be ruled out. What makes the silence especially troubling is that it persists in a universe, otherwise overflowing with structure. Black holes are common, galaxies are everywhere. The physical processes required to build complexity appear robust, and yet intelligence, at least as we can detect it, seems absent. This suggests that the bottleneck may not be astrophysical. It may be biological, or temporal, or something deeper still. The same universe that produces black holes with ease may find it extraordinarily difficult to produce minds that last, and that realization reframes the question entirely. Perhaps the mystery is not why the universe is empty. Perhaps the mystery is why it is not. If the universe is capable of producing complexity, then the silence we observe cannot be explained by absence alone. It must be explained by attrition. Somewhere along the path from matter to mind, the process fails almost every time. This idea is often described as the great filter, not a single obstacle but a sequence of improbable transitions, each one narrow enough that very few worlds pass through all of them. The first filter may lie at the origin of life itself. Chemistry is common, complex molecules form readily in space, but the step from chemistry to biology, from reactions to replication, may be extraordinarily rare. Life may require a precise alignment of conditions that almost never occurs even on habitable planets. If so, the universe could be rich in planets yet poor in life. But Earth complicates this picture. On our planet, life appeared early. Almost as soon as conditions allowed, biology emerged. This suggests that the first step may not be the most difficult. The next filters are less forgiving. For billions of years, life on Earth remained simple. Single-celled organisms dominated while complexity stalled. The transition to multicellular life cells cooperating, specializing, organizing may represent a far more severe bottleneck. This step appears to have occurred only once in Earth's history. Even then, intelligence did not immediately follow. Complex animals existed for hundreds of millions of years before any species began to alter its environment technologically. Intelligence, it seems, is not an inevitable outcome of complexity. And technology is yet another filter. A species may become intelligent without ever becoming industrial. It may adapt perfectly to its environment without needing to reshape it. Tools, fire language, and cumulative knowledge are not guaranteed outcomes of cognition. Finally, there is survival. A technological civilization acquires unprecedented power over its environment and over itself. It gains the ability to reshape a planet, alter a climate, and unleash forces capable of ending its own existence. This stage may be the most dangerous of all. The universe may allow intelligence to arise, but it may not allow it to persist. If civilizations routinely destroy themselves, then the silence we observe is not surprising. It is expected. Yet there is another possibility. The most severe filter may lie behind us. If the early steps, life complexity, intelligence, are all extraordinarily rare, then humanity may already have passed the hardest trials. The silence would then be a consequence of uniqueness, not failure. This distinction matters. If the great filter lies ahead, our future is fragile. If it lies behind, our responsibility is immense. Either way, the conclusion is the same. The universe does not appear optimized for intelligence. And that raises a final unsettling question. If minds are rare in a cosmos shaped by black holes and governed by deep physical law, what does that say about our place within it? Black holes taught us something uncomfortable. Not about violence, not about destruction, but about limits. They reveal that space can end, that time can lose its direction. That information, the most fundamental currency of physics, must be protected at all costs, or the universe itself becomes incoherent. In doing so, they forced physics to reconsider what is truly fundamental. And perhaps they force us to do the same. If spacetime is emergent, then so is everything that unfolds within it. Stars, planets, chemistry, biology, and eventually, if conditions allow, minds. Nothing in this chain appears guaranteed. The universe produces black holes with ease. It produces galaxies in abundance. But it may produce thinking beings only rarely and briefly. If that is true, then intelligence is not the natural outcome of cosmic evolution. It is an exception, and exceptions carry weight. If minds are rare, then meaning is rare. Not in a mystical sense, but in a physical one. The ability to ask questions, to remember the past, to imagine futures that do not yet exist. These may be among the least common phenomena the universe allows. Black holes do not care about this. They form, they persist, they evaporate. The universe continues regardless. But in a cosmos where time can end and space can dissolve into deeper structures, the emergence of awareness is not trivial. It is fragile, temporary, and possibly unique. This does not make humanity central. It makes it responsible. If we are among the few or the only ones, then the future of meaning may depend on choices made within a narrow window of cosmic time. black holes mark the boundaries of what physics permits. Life intelligence and civilization may mark the boundaries of what the universe allows to matter. Understanding black holes is not just about understanding collapse horizons or radiation. It's about learning how close reality itself can come to erasing everything, and how against those odds something capable of understanding the universe still managed to appear. The question is no longer whether the universe has meaning. The question is whether meaning can survive long enough to understand the universe that created it. And that story, unlike the life of a black hole, has not yet reached its horizon. Black holes force us to confront the limits of physics, but they do not end the story. They reveal where our equations fail, where space dissolves into something deeper, and where time itself may lose meaning. Yet they also hint at a larger question, one that black holes alone cannot answer. If space and time emerge from something more fundamental, then they must have emerged once before, not at the center of a collapsing star, but at the beginning of the universe itself. The same mathematical pathologies that appear inside black holes also appear when we rewind cosmic history to its earliest moments. Singularities, infinite densities, the breakdown of familiar laws. This symmetry is not accidental. Black holes may represent the end of time locally. The Big Bang may represent the beginning of time globally. And in both cases, physics falls silent. To understand one may be to understand the other. If we want to know whether the universe truly had a beginning, whether time itself emerged from something deeper, or whether reality existed in some form before space and clocks, then the trail leads forward not to galaxies, but to the very first moments of existence. Black holes taught us how the universe ends things. The next question is unavoidable. How did it begin? Black holes taught physics something deeply unsettling. They showed that time is not guaranteed to continue forever. Inside a black hole, according to our best theories, time does not merely slow down. It comes to an end. Paths that once led forward terminate. Futures collapse into inevitability. This is not a metaphor. It is a prediction written directly into the equations. And once that fact is accepted, a question that physics avoided for generations becomes impossible to ignore. If time can end, can it also have begun? For most of modern cosmology, the answer seemed obvious. The universe began in the Big Bang, time started there, space emerged, everything followed. But this confidence rests on fragile ground. The Big Bang is not a moment we have observed. It is not an explosion caught in the act. It is the point where our equations stop working. When physicists trace the expansion of the universe backward, densities rise, temperatures climb, and time itself shrinks toward a boundary. Eventually, the mathematics points to a singularity, a place where known laws no longer apply. This is where many explanations quietly end. But singularities are not explanations. They are warnings. They tell us that a theory has been pushed beyond its limits, that something essential is missing from our description of reality. Black holes made this lesson unavoidable. Before we understood quantum effects at their horizons, black holes also ended in singularities. They too seem to mark absolute endings. And yet deeper analysis revealed that the story did not stop there. Information survived. Time behaved differently. Space itself became suspect. The singularity was not the answer. It was the signpost. Now cosmology faces the same dilemma. Is the Big Bang truly the beginning of time? Or is it another horizon beyond which our current language fails? Did the universe emerge from nothing? Or did time itself arise from a deeper structure the way space and gravity appear to do near black holes? This series does not assume an answer. Instead, it follows the trail left behind by black holes, objects that force physics to confront its own boundaries, and asks whether the beginning of the universe is as absolute as it appears. Because if time is not fundamental, then asking when the universe began may already be the wrong question. When people hear the phrase Big Bang, they usually imagine an explosion, a flash of light, matter flying outward, a universe born at a single point in space. That picture is wrong. The Big Bang is not an event that happened somewhere in the universe. It is not a blast expanding into empty space. And it's not, strictly speaking, a description of a beginning. In modern cosmology, the Big Bang is a model. It is a mathematical framework that describes a universe which was once extremely hot, extremely dense and expanding everywhere at once. Every region of space was compressed. Every direction was equivalent. There was no center, no edge, and no surrounding void. The expansion did not begin at a point in space. Space itself was already there, just in a very different state. This distinction matters, because when cosmologists speak of the age of the universe, they are not measuring time since creation. They are measuring time since the universe entered a phase we can describe reliably, a phase where particles existed, radiation filled space, and physical laws as we understand them applied. The Big Bang marks the earliest moment where our current theories still work. Not the origin of everything, but the edge of our understanding. This is why the Big Bang is often misunderstood as a beginning. The equations do not describe anything earlier, not because nothing existed, but because the tools break down. Run the equations backward and they point toward higher densities and temperatures. Push them far enough and they produce infinities. Space shrinks. Time approaches zero. But physics has encountered this kind of failure before. Classical mechanics breaks down at atomic scales. Electromagnetism fails inside atoms. Gravity itself becomes incomplete when quantum effects dominate. In each case, the solution was not to accept infinities as real, but to replace the theory with a deeper one. There is no reason to assume cosmology is different. The Big Bang model tells us something profound and well-tested. The universe has a hot, dense past. What it does not tell us is whether that past was the beginning of time itself. To answer that question, we must separate two ideas that are often treated as the same. The Big Bang as a physical description of an early universe, and the Big Bang as the origin of existence. They are not equivalent, and confusing them has hidden one of the most important questions in modern physics, one that only emerges when we stop asking what happened at the Big Bang and start asking why our models stop there at all. If the Big Bang is not a beginning, then why do physicists take it seriously at all? Because something unmistakable happened, not inferred from philosophy, not imagined from theory alone, but written directly into the sky. The first clue is motion. Everywhere we look, galaxies are moving away from one another. The farther they are, the faster they recede. This is not because we occupy a special location, but because space itself is expanding. The pattern is uniform, consistent, and measurable. Reverse that expansion in time and the universe becomes smaller, hotter, and denser. This conclusion does not depend on assumptions about origins. It follows directly from observation. The second clue is light, ancient light. Long after the universe cooled enough for atoms to form radiation that once filled all of space was released and began traveling freely. Today that radiation still surrounds us. It arrives uniformly from every direction, cooled by expansion to just a few degrees above absolute zero. This is the cosmic microwave background. It is not debris from an explosion. It is the afterglow of a universe that was once opaque, hot, and tightly packed. Its spectrum is almost perfectly thermal. Its tiny fluctuations encode the seeds of all future structure galaxies, clusters, and vast cosmic filaments. No alternative model has ever reproduced this pattern so precisely. The third clue lies in chemistry. The early universe forged the lightest elements in specific ratios: hydrogen, helium, and traces of lithium. These proportions are not arbitrary. They depend sensitively on temperature, density, and timing during the universe's earliest moments. Measure those ratios today and they match the predictions of a hot, dense past with remarkable accuracy. Taken together, these lines of evidence leave little doubt. The universe was once very different from how it is now. It was hotter, it was denser, it was simpler. What they do not tell us is why. None of these observations require a moment of creation. They describe a transformation from one state of the universe to another. They confirm a hot beginning to the universe's current phase, not the birth of reality itself. This distinction is subtle but essential. Physics is excellent at reconstructing what followed. It is far less certain about what came before. The Big Bang model explains how the universe evolved from an early hot state into the structured cosmos we see today, but it remains silent on what set those conditions in place, or whether there was ever a moment when time itself first appeared. And that silence is not a flaw, it is an invitation, because once we accept that the evidence points to a hot dense past but not necessarily an absolute beginning, the real question becomes unavoidable. What happens when we push our theories beyond the evidence? Once the evidence is accepted, the next step seems straightforward. Take the equations that describe an expanding universe and run them backward in time. As space contracts, matter crowds closer together. Temperatures rise, energies increase, galaxies dissolve into plasma, atoms break apart, particles lose their identities. The universe becomes simpler, hotter, denser. At first the mathematics behaves well, but push far enough and something unsettling appears. Density grows without bound, temperature diverges, time shrinks towards zero. The equations point to a singularity. This is often described as the beginning of everything, a moment when the universe was infinitely small and infinitely dense, a point where time itself started. But this interpretation mistakes a mathematical failure for a physical event. In physics, infinities are not discoveries. They're alarms. They signal that a theory has been extended beyond the domain where it applies. The equations are still producing numbers, but the numbers have lost meaning. We have encountered this before. Classical physics predicts that atoms should collapse. It predicts infinite energy and radiation fields. It predicts catastrophes that do not occur. Each time the resolution was not to accept the infinity as real, but to recognize the theory's limitation and replace it with something deeper. The Big Bang singularity fits this pattern precisely. General relativity. The theory used to describe the universe's expansion treats spacetime as smooth and continuous. It ignores quantum effects entirely. Near ordinary stars and galaxies, this approximation works extremely well. Near the earliest moments of the universe, it almost certainly does not. When densities approach extremes, quantum fluctuations of spacetime itself can no longer be neglected. The very concepts of distance and duration lose their classical meaning. At that point, the equations are no longer describing reality. They are describing their own breakdown. The singularity then is not evidence of a beginning, it is evidence that the model has reached its limit. This realization forces a shift in perspective. The question is no longer what happened at time zero. It becomes, why does time zero appear at all in our equations? And more importantly, what replaces it? Black holes taught physics this lesson once already. Their singularities seemed absolute, until deeper analysis revealed new structure at their boundaries. Cosmology may be facing the same challenge. If the Big Bang singularity is not a physical origin, but a signpost pointing toward missing physics, then the true history of the universe may extend beyond the boundary we have mistaken for a beginning. And that possibility changes the entire conversation. In physics, a theory is judged not only by what it explains, but by where it fails. Singularities mark those failures with brutal clarity. They are places where numbers explode, predictions vanish, and the language of the theory collapses under its own assumptions. Lengths shrink to zero. Curvatures become infinite. Cause and effect lose meaning. This is not how nature usually behaves. When a physical description produces infinities, it is rarely revealing a feature of reality. More often, it is revealing a flaw in the description itself. History makes this pattern clear. Classical electromagnetism predicted that electrons spiraling around atoms should radiate energy endlessly and collapse into the nucleus. They did not. The resolution was not to accept atomic collapse as real, but to replace classical physics with quantum mechanics. Newtonian gravity predicted that forces become infinite at zero distance. Reality did not comply. General relativity replaced force with geometry, removing the infinity by changing the framework. Singularities appear precisely where frameworks run out of validity. The Big Bang singularity fits this pattern too well to ignore. It arises because general relativity treats spacetime as smooth and continuous at all scales. It assumes that distances can be made arbitrarily small and times arbitrarily short. Near ordinary conditions, this works. Near the extreme densities of the early universe, it almost certainly does not. Quantum mechanics tells a different story. At very small scales, nature resists precise localization. Energy fluctuates. Geometry itself becomes uncertain. The idea of a perfectly defined point in space or a perfectly sharp moment in time ceases to make sense. Combine these insights and a singularity looks less like a physical beginning and more like a boundary imposed by incomplete mathematics. This realization reframes the problem entirely. The question is no longer what emerged from the singularity. It becomes what theory removes the singularity altogether. This is why physicists do not treat the Big Bang singularity as a literal birth event. They treat it as a signpost pointing toward missing physics, just as black hole singularities once did. And this parallel is not accidental. Black holes and the Big Bang are the only known places where spacetime is pushed to its absolute limits. In both cases, these same mathematical pathologies appear. In both cases, general relativity predicts its own breakdown. This suggests a deeper unity. Whatever resolves singularities in black holes may also resolve the apparent beginning of the universe. The singularity is not the story. It is the place where the story stops being told. And when physics encounters silence, it does not stop asking questions. It changes its language. Once singularities were recognized as warning signs rather than answers, cosmology faced a difficult choice. Either accept that the universe truly began at a mathematical breakdown, or search for a deeper framework that could soften the extreme conditions of the early cosmos. The first serious attempt to do the latter came in the form of cosmic inflation. Inflation was not introduced to explain a beginning. It was proposed to solve a set of practical problems, mismatches between observation and theory, that the standard Big Bang model could not easily reconcile. One of these was uniformity. The universe looks remarkably the same in every direction. Regions of space separated by vast distances share nearly identical temperatures and properties, even though, according to simple expansion models, they should never have been in contact. Another was geometry. Space appears almost perfectly flat, balanced delicately between collapse and endless expansion. Without fine-tuned initial conditions, this balance should be extraordinarily unlikely. Inflation offered an elegant solution. It proposed that very early in cosmic history, space underwent a brief but violent phase of accelerated expansion. In a fraction of a second, microscopic regions were stretched to astronomical scales. Irregularities were smoothed out. Geometry was flattened. Tiny quantum fluctuations were magnified into the seeds of galaxies. Inflation worked, at least mathematically. It explained why the universe looks uniform. It explained why it appears flat. It explained how structure could arise from quantum noise. And crucially, it pushed the singularity backward. If inflation occurred before the hot Big Bang phase, then the extreme conditions we extrapolate toward may not represent a true beginning at all. They may describe a transition between regimes, one dominated by inflationary physics and one governed by familiar particles and radiation. For a time, this seemed like progress, but inflation carried a hidden cost. It required conditions of its own, a field to drive expansion, a vacuum-like state with specific properties, a space-time background in which the process could unfold. Inflation did not eliminate the question of origins. It relocated it. Instead of asking what happened at the Big Bang, cosmologists now had to ask what set inflation in motion, and whether inflation itself had a beginning. The escape from the singularity was incomplete. The mathematics had gained flexibility, but the conceptual problem remained. If inflation needs space and time to operate, then it cannot explain the origin of space and time themselves. The beginning had not been removed. It had only been moved out of sight. Inflation changed the story of the early universe, but it did not end it. For all its success, inflation rests on assumptions that often go unspoken. It requires a space-time framework in which expansion can occur. It requires a notion of time so that one moment can follow another. It requires physical laws already in place. In other words, inflation assumes what it does not explain. This becomes clear when we ask a simple question: what existed before inflation? The theory does not say. Some versions suggest inflation could be eternal, occurring repeatedly in different regions. Others treat it as a transient phase triggered by specific initial conditions. But in every case, inflation presupposes a background, some arena in which the process unfolds. That arena is spacetime itself, and this is where the deeper problem emerges. If inflation needs time to run, then it cannot explain the origin of time. If it needs space to expand, then it cannot explain the origin of space. At best, it explains how the universe evolved from an earlier state into the one we observe today. It does not tell us whether there was ever a first moment. This limitation mirrors a lesson learned from black holes. Before quantum effects were considered, black holes appeared to end time completely. The singularity looked final. Only later did physicists realize that the breakdown occurred not in reality but in the theory's assumptions. Inflation may occupy a similar position in cosmology. It smooths the universe. It explains structure. It delays the singularity, but it does not remove the fundamental question: was there ever a moment when time itself began? Or is the appearance of a beginning simply a feature of the models we use? Once this is recognized, the problem of origin shifts again. The question is no longer about what happened at the Big Bang or before inflation. It becomes a question about the nature of time itself. Is time a basic ingredient of reality? Or is it something that emerges like temperature or pressure from deeper processes? If time is emergent, then asking when the universe began may be as misguided as asking where temperature begins in a gas. The apparent beginning could be a boundary of description, not a boundary of existence. And if that is true, then cosmology must confront a far more radical possibility. Time itself may not be fundamental. The question sounds simple: what existed before the Big Bang? But simplicity can be deceptive, because hidden inside that question is an assumption rarely examined. That time is something fundamental, something that must always be present, something that exists independently of the universe it describes. Modern physics gives us reasons to doubt that assumption. In everyday experience, time feels absolute. Seconds pass. Causes precede effects. Memories point backward. Expectations point forward. This intuition is so deeply ingrained that imagining a universe without time feels impossible. Yet physics has repeatedly shown that intuition is a poor guide at fundamental scales. In relativity, time does not tick at the same rate everywhere. It stretches near massive objects. It slows with motion. It can even come to a halt at horizons. There is no single universal clock governing the cosmos. In quantum theory, time plays an even stranger role. It is not an observable in the same sense as position or momentum. It enters equations as a parameter, not as a measurable quantity. The theory works, but only by quietly assuming time rather than explaining it. This tension becomes impossible to ignore in cosmology. If the universe as a whole is treated as a quantum system, then asking how it evolves in time becomes problematic. There is no external clock, nothing outside the universe to measure against. The usual distinction between before and after begins to blur. Some approaches suggest that time is not a primitive ingredient at all. Instead, it may emerge from change, from correlations, from relationships between physical degrees of freedom, from the way different parts of the universe influence one another. In this view, time is not something the universe moves through. It is something the universe generates. If that is true, then asking what happened before the Big Bang may be like asking what is north of the North Pole. The question assumes a coordinate system that ceases to apply. The Big Bang would not mark the first moment of time. It would mark the earliest moment where time as we understand it becomes a useful concept. This idea is unsettling because it strips away a familiar anchor. It replaces a narrative of creation with a boundary of description, not a birth, but a transition from a regime where time has meaning to one where it does not. Black holes hinted at this possibility first. Near their horizons, time behaves strangely. Inside them, it may lose its conventional role entirely. Cosmology now confronts the same behavior but on the largest scale imaginable. The universe may not have begun in time. Time itself may have begun in the universe. And that distinction changes everything that follows. Once time itself is questioned, the universe can no longer be treated as an ordinary physical object. It becomes a system without an external reference frame. No outside clock, no external observer. This is where quantum cosmology enters the story. In this approach, the universe is described using the rules of quantum mechanics, not as a collection of particles moving through space and time, but as a single quantum system governed by probabilities and correlations. At this scale, familiar concepts begin to dissolve. The geometry of space is no longer fixed. The flow of time is no longer continuous. Even the notion of a definite history becomes uncertain. Instead of a single, sharply defined beginning, quantum cosmology often predicts a range of possible early states. The universe does not emerge from a point of infinite density. It transitions from a regime where classical spacetime simply does not apply. In some models, the singularity disappears entirely. There is no moment when density becomes infinite, no instant when time suddenly switches on, no boundary separating nothing from something. What replaces the singularity is not an event but a quantum phase, one governed by uncertainty rather than breakdown. This does not mean the universe came from nothing. It means the question is framed incorrectly. In quantum mechanics, systems do not always have well-defined properties until they are measured or constrained. Asking for a precise beginning in time may be demanding a level of definition that reality does not provide. From this perspective, the Big Bang is not the start of existence. It is the moment when classical spacetime becomes a good approximation. When quantum fluctuations of geometry settle into something that can be described by distances, durations, and expansion, the beginning fades not into mystery but into abstraction. This shift is subtle but profound. It replaces a narrative of creation with a narrative of emergence. Not a universe born at an instant, but a universe crystallizing into form. And yet this resolution comes at a cost. Quantum cosmology does not offer a single definitive picture. It offers families of models, each extending beyond classical boundaries in different ways. Some predict smooth beginnings, others suggest bounces, still others imply timeless phases with no clear ordering at all. What unites them is not certainty but restraint. They refuse to place an absolute beginning where physics has no justification for one. The vanishing beginning is not a failure of explanation, it is a refusal to invent one, and that restraint may be the most honest response physics can offer when confronting the deepest questions it knows how to ask. Once the singularity fades, a new class of possibilities comes into view. Universes that do not begin. This idea runs against almost every human intuition. In daily life, things start. Events have causes. Stories have opening lines. It feels unnatural to imagine a reality without a first moment. Physics, however, is not required to respect narrative instincts. Several cosmological models now explore the possibility that the universe did not originate at a single point in time, but transitioned from an earlier phase or has existed in some form indefinitely. One possibility is a bounce. Instead of emerging from an initial singularity, the universe may have passed through a phase of contraction before rebounding into expansion. Density increases, quantum effects dominate, and collapse is halted not by a breakdown but by new physics. The universe does not begin, it turns around. In this picture, the Big Bang is not birth. It is a transition. Another possibility is eternal inflation. Here inflation never truly ends. Different regions of space stop inflating at different times, forming local universes like bubbles in a vast ever-expanding background. Each bubble has its own hot Big Bang-like beginning, but the overall process has no global start. Beginnings exist locally, not universally. There are also cyclic models, where the universe undergoes repeated phases of expansion and contraction. Each cycle resets conditions while the larger structure persists across immense spans of time. None of these models is confirmed. None can yet be ruled out. What matters is not their certainty, but their implication. They demonstrate that a universe consistent with known physics does not require an absolute beginning. Time can be extended, reset, reinterpreted. The appearance of a start may emerge from limited perspective rather than fundamental necessity. This reframes the Big Bang once again. It becomes a feature of our observable patch, not a statement about all of existence. And with that reframing comes a deeper challenge. If the universe has no first moment, why does it look so young? Why does it have a finite age? Why does time appear to flow in one direction at all? These questions point toward something even more fundamental than beginnings. They point toward entropy. If the universe has no first moment, then one question becomes unavoidable. Why does it appear to have an age? Everything we observe suggests a timeline. Galaxies evolve. Stars are born and die. Light carries a record of the past. The universe looks different at different distances, as if we are peering backward through time. This impression is so strong that it is often mistaken for proof of a beginning, but age and origin are not the same thing. A system can have a measurable age without having a true start. What we call the age of the universe is really the duration of its current phase, the time since it entered the state we can observe and describe. The deeper question is why that phase exists at all. In an eternal or cyclic universe, there may be countless earlier phases hidden beyond observational reach. If so, why does our observable region look so ordered, so structured, and so far from equilibrium? The answer points toward entropy. Entropy is often described as disorder, but this is misleading. More precisely, it measures how many microscopic arrangements correspond to the same large-scale appearance. High entropy means many possible configurations. Low entropy means very few. The universe today has high entropy compared to its past. Stars burn fuel, energy spreads, structures dissolve. This trend gives time its direction. But the early universe was different. It was remarkably smooth, uniform, and low in entropy. Matter was evenly distributed. Gravitational clumping had barely begun. From a statistical perspective, this state was extraordinarily special. This is the real mystery. Not why the universe expanded, not why it cooled, but why it began in such an improbably ordered condition. If the universe were eternal and chaotic, we would expect to observe a random high-entropy state. Instead, we see a cosmos poised delicately at the start of complexity. This suggests that the arrow of time did not emerge automatically. It was set, whether by boundary conditions, deeper laws, or processes we do not yet understand. The universe entered its current phase in a state that allowed entropy to increase and time to flow. And once entropy begins to rise, history unfolds. The universe looks young not because it was created recently, but because it is still far from equilibrium. This realization shifts the problem of beginnings once again. The question is no longer when did the universe begin? It becomes why did time acquire a direction at all? And answering that requires looking not at expansion but at information. Nothing in the fundamental laws of physics prefers a direction. At the deepest level, we know how to describe the equations of motion work just as well, forward as backward. Reverse time in the mathematics and the laws do not object. Particles still move, forces still act. The rules remain intact, and yet reality clearly does not behave this way. Eggs break but do not unbreak. Smoke spreads but does not reassemble. Memories point toward the past, never the future. Time has a direction. This direction is not written into the laws themselves. It emerges from entropy. Entropy increases because there are overwhelmingly more disordered states than ordered ones. A system that begins in a special low entropy condition will almost certainly evolve towards states that are more typical, more probable, and less constrained. This statistical tendency gives time its arrow, but here is the unsettling part. The laws of physics do not explain why the universe began in a low entropy state. They simply assume it. The early universe was extraordinarily smooth. Matter was distributed with astonishing uniformity. From the perspective of gravity, this is not disorder, it is extreme order. Countless other configurations were possible, and almost all of them would have higher entropy. The universe did not have to start this way, yet it did. This is the deepest puzzle in cosmology, not why entropy increases, but why it had room to increase at all. If the universe were eternal and unstructured, we would expect to find ourselves in a high entropy state surrounded by randomness. Instead, we observe a cosmos finely poised for complexity, structure, and history. The arrow of time was not inevitable. It was enabled. Some explanations appeal to boundary conditions. Others suggest that entropy is reset through cosmic cycles or bounces. Still others propose that the low entropy past is a selection effect, that we could only exist in a universe where time flows in a way that permits memory and evolution. None of these answers is complete. What they share is an admission. The direction of time is not a consequence of expansion or creation. It is a consequence of information, how it is arranged, preserved, and allowed to spread. Black holes brought this into focus once before. They forced physics to confront the fate of information at the edge of spacetime. Cosmology now faces the same challenge, but on the scale of the universe itself. Understanding why time has a direction may require understanding why information was once so tightly constrained, and that question reaches beyond beginnings. It reaches into the structure of reality itself. Every explanation of time eventually collides with the same obstacle. Why did the universe begin its observable history in such an extraordinarily low entropy state? This is not a minor technical issue. It is not a detail to be refined with better data. It is a structural question, one that sits beneath inflation, beneath quantum cosmology, and beneath every model that attempts to avoid a singular beginning. The early universe was not just hot and dense, it was improbably ordered. From a statistical standpoint, almost any other configuration would have been more likely. Matter could have been clumped. Gravity could have already formed black holes. Entropy could have been near its maximum. None of that happened. Instead, the universe began in a condition that allowed structure to form, stars to ignite, chemistry to unfold, and time to acquire a direction. This is not explained by the known laws of physics. The equations tell us how entropy evolves once conditions are set. They do not tell us why those conditions were chosen. Several responses have been proposed. One approach treats the low entropy past as a boundary condition, an unexplained input to the theory. The universe simply was this way, and physics proceeds from there. This answer is mathematically consistent but deeply unsatisfying. Another approach appeals to selection effects. Perhaps many universes exist, each with different initial conditions. We observe a low entropy past because only such universes permit observers capable of noticing anything at all. This explanation shifts the mystery rather than resolving it. It replaces a single improbable state with a vast ensemble whose existence cannot be independently tested. There are also dynamical proposals, ideas in which entropy is reset through cosmic cycles, bounces or transitions between phases. In these models, the universe may spend most of its existence in high entropy states, occasionally passing through rare low entropy bottlenecks. But here too the problem resurfaces. Why do such bottlenecks exist at all? Why does the universe ever return to a special state? The uncomfortable truth is that cosmology currently lacks a compelling explanation for the low entropy past. This is not a failure of imagination. It is a limit of understanding. The problem resists resolution because it sits at the intersection of gravity, quantum mechanics, and information theory domains that have not yet been unified into a single framework, and so the question remains, not how the universe evolved, but why it was able to evolve in the first place. This is the point where many narratives quietly stop. But stopping here would miss a crucial insight, because the same question about entropy information and special initial conditions has already appeared somewhere else in physics. At the edge of a black hole. At first glance, black holes and the Big Bang seem to belong to opposite ends of the universe. One marks collapse, the other expansion. One appears to end time, the other appears to begin it. Yet when examined through the lens of physics, the distinction becomes less clear. Both arise from the same equations, both lead to singularities, both signal the breakdown of classical spacetime. In a black hole, matter falls inward, entropy increases, and the future becomes constrained. All possible paths point toward a region where known laws fail. Time in a very real sense runs out. In the early universe, matter expands outward. Entropy also increases and the past appears constrained. All possible histories trace back toward a region where known laws again fail. The symmetry is striking. In one case, the singularity lies in the future. In the other, it lies in the past. This has led physicists to ask whether these two extremes are related more deeply than analogy suggests. If a black hole can be thought of as a local end of time, then the Big Bang may be thought of as a global version of the same phenomenon, time approaching a boundary beyond which our description collapses. But there is a crucial difference. Black holes form within an already existing universe. Their horizons hide information, but quantum effects appear to preserve it. What looks like destruction may instead be extreme rearrangement. If the same principle applies to the Big Bang, then the apparent beginning may not be creation from nothing. It may be a horizon separating two regimes of description. On one side, classical spacetime applies, on the other it does not. In this view, the Big Bang is not the first moment of existence. It is the earliest moment we can describe using spacetime at all. The low entropy past then takes on a new meaning. Just as black holes impose strong constraints on information at their horizons, the early universe may have been constrained by conditions analogous to a horizon in time. Information was not random, it was restricted, structured, compressed into a highly special configuration. This does not solve the problem of initial conditions, but it reframes it. The question is no longer why the universe began in a special state. It becomes why transitions between regimes of physics impose such strong informational constraints. Black holes taught us that horizons are not empty boundaries. They encode information, they regulate what can pass and what cannot. If the Big Bang is a kind of temporal horizon, then its role may be similar, not to create the universe, but to regulate the conditions under which time, entropy, and structure emerge. This idea remains speculative, but it carries a powerful implication. The deepest puzzles of cosmology may not be about beginnings or endings at all. They may be about boundaries. Human intuition is built on beginnings. Lives begin, stories begin, events unfold from a first cause. This way of thinking is so deeply ingrained that a universe without a beginning feels almost incoherent. It seems to demand explanation in the same way a sentence demands a first word. But physics is not obligated to respect narrative structure. There are many systems in mathematics and nature that do not possess a starting point, even though every local event within them has a cause. The sequence of integers has no first number. A circle has no privileged point of origin. Yet both are perfectly well defined. The universe may be similar. In a cosmos without a beginning, every moment could be preceded by another without the chain terminating at a first link. Time would not emerge from nothing. It would extend indefinitely, structured by laws rather than anchored to an origin. This idea does not deny causality. It removes the need for a first cause. In such a universe, the Big Bang would still exist, but not as an absolute beginning. It would mark a transition, the onset of a phase where spacetime behaves classically, where entropy can grow, and where history becomes meaningful. Earlier phases might obey different rules. Time could exist in a form unrecognizable to us, or not exist at all in any familiar sense. This challenges more than physics. It challenges the expectation that explanations must terminate in a single definitive moment, that reality must answer why there is something rather than nothing, in a way that satisfies human preference for closure. Physics offers no such guarantee. It describes patterns, it identifies constraints, it reveals what is allowed and what is forbidden. Whether the universe had a beginning may not be a question. Physics can settle decisively. It may be a category error, a demand for an answer where the framework itself does not permit one. This does not weaken cosmology. It clarifies its limits, and within those limits lies a quieter, more unsettling possibility. The universe may not have started. It may simply be, and if that is the case, then the absence of a beginning is not a failure of explanation. It is a feature of reality. Every scientific theory is built on an agreement about what can be measured, about what can be observed, about what questions can be meaningfully asked. Cosmology pushes these agreements to their limits. When we ask whether the universe had a beginning, we're no longer asking about galaxies, radiation, or particles. We're asking about conditions that may lie forever beyond observation. No signal can reach us from before the earliest transparent moments of the universe. No experiment can recreate the energies involved. Physics must work with what is accessible. This does not mean it is powerless. It means it is constrained. Theories can be extended. Models can be refined. Mathematics can explore possibilities far beyond current data. But without observational anchors, certainty fades. This is not unique to cosmology. No experiment can directly observe the inside of a black hole. No measurement can access the exact state of the universe as a whole. No observer can stand outside spacetime to watch it unfold. In these regimes, physics becomes a discipline of consistency rather than verification. Models are judged by whether they agree with known laws, reduce contradictions, and connect smoothly to observable reality. But multiple models can satisfy these criteria. A universe with a beginning, a universe without one, a universe that cycles, a universe that inflates eternally. Physics may never select a single answer, not because it has failed, but because nature does not offer a definitive test. This is an uncomfortable conclusion. It challenges the expectation that every question has a final factual resolution, that science always converges to a single narrative. Yet this expectation has never been guaranteed. Physics does not promise ultimate answers. It promises reliable ones within defined domains. Beyond those domains, it offers frameworks, constraints, and possibilities. It tells us what is consistent, what is forbidden, and what remains undecidable. The question of cosmic beginnings may belong to this last category, not unknowable in principle, but underdetermined by evidence. This does not render the question meaningless. It renders it humbling. It reminds us that explanation has limits, not because reality is mysterious, but because observation is finite. And once those limits are acknowledged, the focus shifts again. If physics cannot tell us definitively whether the universe began, what can it still tell us? Quite a lot. The absence of a final answer does not mean the absence of progress. Even when physics cannot tell us how the universe began, or whether it began at all, it continues to teach us something equally important: how reality is structured and how far explanation can reach. By probing the limits of cosmology, we've already learned that space and time are not as fundamental as they appear. They behave differently under extreme conditions. They may emerge from deeper principles tied to information entropy and quantum structure. These insights did not require knowing the ultimate origin. They emerge from asking what fails, where it fails, and why. Black holes taught us that horizons regulate information. Cosmology taught us that early conditions regulate time's direction. Both reveal that boundaries, not events, often shape reality. This shift matters. It moves the focus away from singular moments and towards structural constraints. Instead of asking what happened first, physics asks what must always be true for the universe to behave as it does. What kinds of laws permit stable spacetime? What conditions allow entropy to increase? What structures enable complexity to persist? These questions can be explored even when origins remain uncertain. They connect cosmology to other fields, quantum information, statistical mechanics, and the study of complexity itself. They reveal that the universe is not defined solely by how it began, but by how it maintains coherence across vast scales of space and time. There is also a subtler lesson. Unanswered questions expose the assumptions we did not realize we were making. They force us to examine not just the universe, but the conceptual tools we use to describe it. In this sense, the mystery of beginnings is productive. It prevents premature closure. It resists oversimplification. It keeps inquiry alive. Physics advances not only by solving problems, but by discovering which problems cannot yet be solved and why. And that awareness shapes how we interpret everything else we learn, including our place within the universe. If time is not fundamental, then neither is anything that depends on it. Stars require time to form. Planets require time to stabilize. Life requires time to experiment, fail, and adapt. If the universe entered its current phase through a narrow set of conditions that allowed entropy to rise gradually rather than all at once, then everything that followed was contingent. Nothing was inevitable. A universe without a clear beginning does not imply abundance. It implies fragility. If time emerged from special conditions, then complexity emerged from those conditions as well. Chemistry, biology, and intelligence are not generic outcomes of cosmic evolution. They are rare trajectories through an immense space of possibilities. Most histories lead nowhere interesting. They expand, cool, and dissolve. They rush toward equilibrium without ever forming structure. They never slow enough for complexity to take hold. The universe we observe avoided those outcomes, but only briefly. Structure exists in a narrow window. Stars burn for a finite time. Planets remain habitable for a fraction of cosmic history. Even intelligence, once it appears, may be transient. This reframes the problem of meaning. Meaning does not arise because the universe was designed to produce it. It arises because certain configurations of matter and information briefly permit it. If the universe had a beginning, that beginning did not guarantee intelligence. If the universe had no beginning, eternity did not guarantee it either. Either way, awareness is not typical. This is why questions about origins matter even when they remain unanswered. They reveal how contingent our existence is, how dependent it is on conditions that could easily have been different. In a universe where time itself may be emergent, the appearance of minds capable of reflecting on time is doubly rare. First, time had to exist in a usable form. Then, within that time, complexity had to survive long enough to become aware of itself. This does not grant humanity cosmic importance. It grants it cosmic improbability, and improbability carries consequences. The universe does not ask to be understood. It does not adjust its behavior to fit human intuition. It does not simplify itself for explanation. And it does not promise answers to every question we learn to ask. This is not a failure of science. It is a feature of reality. Cosmology reveals a universe governed by constraints rather than intentions. Laws operate without preference. Processes unfold without regard for observers. The cosmos expands, structures form. Entropy increases whether or not anyone is there to notice. From this perspective, the absence of a definitive answer about cosmic beginnings is not an anomaly. It is expected. The universe does not owe us an origin story. It does not owe us a first moment. It does not owe us closure. What it offers instead are patterns, regularities that can be tested, refined, and connected into coherent frameworks. Physics does not uncover ultimate meaning. It uncovers consistency, and consistency is enough to build understanding. This realization forces a shift in expectations. Science is not a path toward absolute certainty. It is a method for navigating uncertainty responsibly. When multiple models remain viable, physics does not choose based on narrative appeal. It chooses based on internal coherence, empirical reach, and restraint. Where evidence ends, speculation must remain disciplined. This discipline is often mistaken for pessimism. It is not. It is respect for the difference between what can be known and what can only be imagined. In accepting that the universe may not provide final answers, cosmology does not diminish human curiosity. It sharpens it. It directs attention toward questions that can be explored meaningfully even when ultimate origins remain unresolved. And within that exploration lies a quieter insight. Meaning does not arise because the universe supplies it. It arises because conscious systems extract it. In a cosmos indifferent to explanation, the act of understanding becomes significant, not because it is demanded, but because it is chosen. If the universe had a beginning, it left no clear trace of it. If it did not, it offers no obvious alternative. In either case, the story does not resolve into a single answer. It dissolves into structure, constraint, and possibility, into a reality that resists being compressed into a moment. This is not a weakness of cosmology. It is its most honest outcome. Black holes taught us that time can end without warning. The early universe taught us that time can emerge without explanation. Between these two boundaries lies everything we know. Stars form, galaxies evolve. Life appears briefly in pockets of order carved out of entropy's rise. Whether time began or merely became useful may never be decided conclusively. The evidence may always be compatible with more than one story. The universe may simply refuse to choose, but that refusal carries meaning of its own. It tells us that reality is not obligated to fit the categories we prefer, that beginnings and endings may be features of description, not of existence, that the deepest questions are sometimes those that reshape how we ask them. In a universe that may have no first moment understanding becomes a local achievement, temporary, context dependent, yet no less real for that. We ask questions not because the universe demands them, but because we exist at a rare intersection, where time flows, where memory persists, and where matter has arranged itself into something capable of wondering how it all began. If time truly emerged, then so did curiosity. And if the universe does not provide a final answer that does not render the question pointless, it makes the act of asking part of the story itself. What began may not be time, but the search for understanding clearly did. For most of its existence, the universe did not think. It expanded. It cooled. It formed stars, galaxies, and black holes without awareness, without intention, without experience. For billions of years, nothing in the cosmos noticed any of it. Physics worked perfectly well without observers. Gravity sculpted structure. Entropy increased. Time flowed in one direction. No witness was required. And yet at some point very late in cosmic history, something profoundly unnecessary happened. The universe began to be aware of itself. Not everywhere, not all at once, but in small fragile regions where matter arranged itself into systems capable of processing information, storing memories and modeling their own existence. This was not demanded by any physical law. Nothing in cosmology requires consciousness. Nothing in particle physics predicts experience. Nothing in the expansion of space points inevitably toward awareness. And that is what makes the question unavoidable. If time can emerge from deeper structure as modern physics increasingly suggests, then consciousness presents an even stranger puzzle. It is not just a feature of matter. It is a feature of organized information appearing only under extraordinarily specific conditions. Most matter never thinks. Most complexity never reflects. Most of the universe remains permanently mindless. So why did awareness appear at all? Was it an accident of evolution? A rare side effect of survival strategies? Or an emergent property waiting silently for the right configuration of matter and energy? This series does not begin with brains or biology. It begins with absence, with a universe that functioned flawlessly for billions of years, without perception, meaning, or inner experience, and then briefly produce something capable of asking how it all began. Understanding consciousness is not about placing minds at the center of the cosmos. It is about explaining why the cosmos ever produced minds in the first place. Because if the universe does not need consciousness, then its appearance tells us something deep, not about intention, but about constraints information and the narrow path through which complexity can pass. The question is no longer what is consciousness. The question is far more unsettling. Why did a universe that never needed to be aware become aware at all? For most of its history, the universe functioned without perception. Galaxies formed and collided, stars ignited and burned out, black holes grew, merged and evaporated. None of this required a witness. The laws of physics do not depend on observation to operate. Gravity does not wait to be seen. Thermodynamics does not require interpretation. Entropy increases whether or not anything is there to notice it. This is a crucial starting point, because it immediately dismantles a quiet assumption. Many narratives carry that consciousness is somehow central to how the universe works. It is not. The universe is not built around minds. It is not optimized for experience, and it does not fail in their absence. For billions of years after the Big Bang, there were no planets, no chemistry complex enough for life, and certainly no nervous systems. Yet the cosmos evolved with remarkable consistency. Structure emerged, energy flowed, time acquired direction. Nothing was missing. Even today, the overwhelming majority of the universe remains permanently unaware. Vast regions of space contain nothing but thin gas and radiation. Most matter is locked inside stars or drifting between them. Most processes unfold in silence. From a physical perspective, this is the default state. Mindlessness is not an exception. It is the norm. This matters because it reframes the problem of consciousness. If awareness were a fundamental feature of reality, we might expect to see traces of it everywhere, embedded in particles, written into fields, required for physical law to make sense. We see none of that. Consciousness appears only in very specific environments on at least one planet around one star in one small corner of one galaxy. It is local, fragile, and latent. Nothing in cosmology predicts it. Nothing in fundamental physics demands it. This suggests a sobering possibility. Consciousness is not a building block of the universe. It is a consequence of rare arrangements within it. The universe does not need minds to exist. But minds need an extraordinarily cooperative universe to arise. Understanding awareness then does not begin with introspection or philosophy. It begins with acknowledging how unnecessary consciousness truly is to everything else that exists. Only by starting from that absence can we properly ask why it appeared at all. Before consciousness can be explained, it must be carefully stripped of the meanings often assigned to it. Because much of the confusion surrounding awareness comes not from what we do not know, but from what we assume without justification. Consciousness is not a substance. It is not something added to matter when complexity reaches a certain level, like an ingredient poured into a finished system. There is no particle of awareness, no hidden field that suddenly switches on. Consciousness is not energy. It cannot be measured in joules. It does not flow or dissipate like heat. Increasing energy does not increase awareness, and most energetic processes in the universe remain entirely mindless. Consciousness is not intelligence. Systems can solve problems, optimize behavior, and adapt to environments without any evidence of subjective experience. Evolution produces efficient strategies long before it produces reflection, and consciousness is not inevitability. There is no known physical law that points toward awareness as an outcome. The equations that describe matter forces in spacetime make no reference to experience. They operate perfectly well without it. This matters because explanations fail when they begin from the wrong premise. If consciousness is treated as something fundamental, analysis stalls. If it is treated as mystical, inquiry stops altogether. If it is assumed to be universal, its rarity becomes inexplicable. A scientific approach requires restraint. It does not deny experience. It does not dismiss subjectivity. But it insists that whatever consciousness is, it must arise from physical processes with observable consequences. That means starting with what can be studied: information processing, feedback loops, memory, integration across time. These are not definitions of consciousness. They are constraints features that any viable explanation must account for. By removing what consciousness is not, the problem becomes clearer. We are not asking why matter has awareness. We are asking under what conditions matter behaves in ways that give rise to experience. That shift is subtle but essential. It moves the question out of metaphysics and into physics, biology, and information theory, where progress, however slow, is still possible. Only once the ground is cleared can we begin to ask how something as improbable as awareness could emerge from a universe that neither required nor predicted it. If consciousness were a natural outcome of cosmic evolution, we would expect it to appear early. It did not. For nearly the entire lifespan of the universe, there was no awareness of any kind, no perception, no memory, no experience. The cosmos expanded and cooled in silence, governed solely by physical law. The first stars formed hundreds of millions of years after the Big Bang. Galaxies took shape slowly over billions of years. Heavy elements necessary for chemistry, planets, and life were forged only after generations of stellar death. Even then, nothing thought. Life on Earth emerged early relative to planetary history, but it remained simple for an extraordinarily long time. Single-celled organisms dominated for billions of years, evolving, replicating, and surviving without anything resembling awareness. Complex multicellular life arrived late, nervous systems arrived later still, and reflective consciousness. The ability to model the world, remember the past, and imagine the future appeared only in the final fraction of cosmic time. By any reasonable measure, awareness is a latecomer. This timing matters. It suggests that consciousness is not an automatic byproduct of matter or complexity. The universe had countless opportunities to produce it, and almost always did not. Stars formed without minds. Planets orbited without witnesses. Ecosystems evolved for eons without reflection. Awareness required a very specific convergence of conditions, stable environments lasting hundreds of millions of years, energy sources that were reliable but not destructive, biological systems capable of integrating information across time and space. Miss any one of these and consciousness never appears. The lateness of awareness is not an accident of history. It is evidence of constraint. Most paths through cosmic evolution do not lead to minds. They lead to equilibrium, dissipation, or simple repetition. Only a narrow set of trajectories pass through the window where awareness becomes possible. This reframes the question once again. We're not asking why consciousness exists everywhere. We're asking why it exists at all, given how much of the universe functioned perfectly well without it, and continues to do so. The answer, whatever it is, will not be found in the earliest moments of the cosmos. It will be found in the slow accumulation of structure information and constraint long after the universe had already decided how to behave. If consciousness was simply a property of matter, it would be everywhere. Every atom would carry it. Every star would express it. Every sufficiently massive object would at some level be aware. This is not what we observe. The same atoms that form brains also form rocks. The same particles that carry thoughts also drift through interstellar space. Matter alone is not the difference. The difference lies in how matter is organized. This is where the problem of consciousness quietly shifts domains from physics of substances to physics of information. Information is not material in the ordinary sense. It is a description of structure, correlation, and constraint. It tells us not what something is made of, but how its parts relate to one another, and how those relationships change over time. A book and a pile of ash can contain the same atoms. Only one contains information. A brain and a block of stone obey the same physical laws. Only one continuously processes signals, stores memories, and updates internal models. Consciousness, whatever its deeper explanation turns out to be, appears only in systems that do all three. They process information across many scales. They integrate signals from diverse sources. They maintain internal states that persist through time. This immediately explains something that otherwise seems paradoxical: why complexity alone is not enough. The weather is complex. Stars are complex. Galaxies are complex. None of them are conscious. They lack the specific kind of informational organization that binds past, present, and possible futures into a single unified process. This reframing is crucial. It means consciousness is not something added to matter. It is something that emerges when matter enters a narrow class of informational regimes. And those regimes are rare. They require systems that are neither rigid nor chaotic, neither frozen nor explosive, neither isolated nor overwhelmed. They must exist at the edge where information can flow without dissolving, where memory can persist without locking the system in place. Seen this way, awareness is no longer mysterious in the way it once was. It is not supernatural, it is not universal, and it is not inevitable. It is a consequence of matter doing something very specific, something the universe almost never asks it to do. The universe is full of complexity. Stars contain turbulent interiors where nuclear reactions unfold under immense pressure. Galaxies host billions of interacting systems shaped by gravity across vast distances. Weather patterns on planets exhibit chaos feedback and sensitivity to initial conditions, and yet none of these systems think. This tells us something crucial. Complexity alone does not produce consciousness. A system can be dynamic, nonlinear, and richly structured and still lack any form of awareness. The missing ingredient is not scale or activity, but the way information is organized and constrained. Most physical systems disperse information. Energy flows in, interactions occur, and correlations quickly decay. Past states are forgotten. Future states are not anticipated. The system reacts, but it does not model. A conscious system behaves differently. It does not merely respond to the present. It preserves traces of the past, and it uses those traces to influence future behavior. This requires stability. Too much order and nothing changes. Too much chaos and nothing lasts. Stars are too violent. Weather systems are too unstable. Galaxies are too diffuse. Their internal processes never settle into structures capable of maintaining long-term informational coherence. Patterns appear, but they do not persist in a form that can be referenced, compared, or integrated. In contrast, biological nervous systems operate in a narrow regime. Signals propagate reliably but not rigidly. Memories endure but remain plastic. Information is neither erased immediately nor frozen permanently. This balance is extraordinarily difficult to achieve. It depends on chemistry, temperature, energy flow, and evolutionary history aligning just right. Miss the window and matter remains permanently mindless, no matter how large or energetic it becomes. This explains why awareness is not scattered across the cosmos. It is not hiding in stars. It is not diffused through space. It does not emerge simply because enough particles interact. Consciousness requires architecture, not just activity, and architecture is rare. Most matter never thinks because most matter never enters the narrow informational regime where thinking is even possible. That is not a limitation of matter. It is a limitation imposed by physics itself. It is tempting to think that evolution was working toward consciousness. That awareness was an endpoint, a destination reached after enough complexity accumulated, a reward for survival across deep time. This intuition is misleading. Evolution has no foresight, it does not plan, and it does not value understanding. Natural selection operates on a single criterion: differential survival and reproduction. Traits persist not because they are insightful, meaningful, or reflective, but because in a specific environment they increase the chances of continuation. Most successful organisms on Earth have no consciousness in any familiar sense. Bacteria dominate the biosphere. Plants thrive without awareness. Insects exhibit sophisticated behavior with minimal internal modeling. For billions of years, life flourished without anything resembling reflective experience. This alone tells us something important. Consciousness is not required for survival. In many contexts, it may even be a disadvantage. Awareness is slow. It consumes energy. It introduces hesitation where reflex would suffice. A system that thinks too much can lose to one that reacts instantly. Evolution does not reward contemplation. It rewards adequacy. When nervous systems first appeared, they did not bring awareness with them. They brought coordination, faster responses, more flexible behavior. Consciousness, if it emerged at all, did so later piggybacking on mechanisms that evolved for entirely different reasons. This reframes the role of evolution. Natural selection did not create consciousness. It tolerated it. In specific environments under specific pressures, the side effects of increasingly complex information processing may have crossed a threshold, one where internal modeling became useful enough to offset its costs. Awareness in this view is not an evolutionary triumph. It is an evolutionary contingency, a fragile outcome of historical paths that could easily have diverged. Change the environment slightly, alter the constraints, and the trajectory bypasses consciousness entirely. This explains why even today intelligence and awareness do not align cleanly. Systems can solve problems, navigate spaces, and optimize outcomes without any clear evidence of subjective experience. Evolution builds tools, it does not build observers. If consciousness appears, it does so not because evolution sought it, but because under rare conditions the machinery of survival accidentally produced something that could look back at itself. Whatever consciousness turns out to be, it does not escape physics. Brains are not special substances. They are not exempt from thermodynamics. They do not operate outside the flow of energy and entropy. A brain is matter arranged into a particular kind of machine. It consumes energy continuously. It generates heat. It obeys the same physical constraints as any other system in the universe. This fact is easy to overlook because experience feels immaterial. Thoughts have no weight. Memories have no temperature. Awareness seems detached from the machinery that supports it, but this impression is misleading. Every mental state corresponds to a physical state. Every perception involves electrical and chemical activity. Every memory requires energy to store and maintain. From a thermodynamic perspective, brains are engines. They take in low-entropy energy chemical potential stored in food and convert it into organized activity, exporting entropy back into the environment as heat. Without this constant energy flow, neural organization collapses and awareness disappears. There is no mystery here. When energy supply stops, consciousness fades. When neural structure degrades, experience fragments. When physical processes are disrupted, awareness does not persist elsewhere. This grounding matters because it rules out an entire class of explanations. Consciousness is not floating above the brain. It is not added on after the fact. It does not survive independently of the physical system that generates it. At the same time, reducing the brain to just matter misses the point. What matters is not the material itself, but the pattern it sustains. The brain maintains an extraordinarily delicate balance. Stable enough to preserve information, flexible enough to adapt, and energetic enough to update its internal state in real time. Very few physical systems operate in this regime. Too rigid and nothing new can be learned. Too noisy and nothing can be remembered. Brains exist precisely at the edge where energy flow supports long-lived informational structure without destroying it. This is not an accident of design. It is a rare physical configuration that evolution happened to exploit. Understanding consciousness then requires no appeal to forces beyond physics, but does require taking physics seriously, especially where energy, entropy, and information intersect. And once that is acknowledged, a new question becomes unavoidable. If awareness is a physical process, then it is not free. It has a cost. Awareness is not free. From a physical standpoint, consciousness is one of the most energy-intensive strategies evolution has ever produced. Brains demand a constant supply of fuel, oxygen, and stable conditions. They fail quickly when that supply is interrupted. This alone sets a hard limit on where awareness can exist. On Earth, the human brain accounts for only a small fraction of body mass, yet it consumes a disproportionate share of total energy. Even at rest, neural activity continues relentlessly, maintaining internal models, updating expectations, suppressing noise. This is not optional overhead. A conscious system cannot simply power down without losing the very processes that define awareness. Memory must be refreshed, signals must be integrated, predictions must be revised. All of this costs energy. In evolutionary terms, the cost must be justified. For many organisms, it is not. Fast reflexes outperform deliberation in simple environments. Fixed responses work better than flexible ones when conditions are stable. In such cases, awareness provides little advantage and significant risk. A system that hesitates can be outcompeted by one that reacts instantly. This explains why consciousness is not widespread even among complex life. Many animals exhibit remarkable intelligence without clear evidence of reflective awareness. They navigate environments, solve problems, and adapt behavior efficiently without maintaining a persistent internal narrative. Awareness becomes useful only under specific pressures, environments that change unpredictably, social systems that reward modeling other agents, situations where past experience must be weighed against uncertain futures. Even then, the benefit is marginal and fragile. If energy becomes scarce, awareness is one of the first things to be reduced. When organisms are stressed, injured, or deprived, consciousness narrows or disappears entirely. Survival takes precedence over reflection. This reveals something fundamental. Consciousness is not an evolutionary upgrade in the usual sense. It is a costly trade-off. It persists only where the environment reliably supplies the resources needed to sustain it, and where its advantages outweigh its liabilities. In most regions of the universe, those conditions never arise. Energy is either too diffuse or too violent. Stability is either absent or short-lived. Complex chemistry never lasts long enough to support long-term informational structure. The universe does not suppress awareness. It simply makes it expensive, and expense limits abundance. There is a quiet assumption woven into many discussions about the future of life and intelligence, that if a system becomes complex enough, consciousness will eventually appear. That awareness is the natural endpoint of information processing, that given sufficient time, matter will almost inevitably begin to experience itself. Physics offers no such guarantee. Complexity does not point in a single direction. It branches, it multiplies possibilities rather than narrowing them. For every complex system that supports awareness, there are countless others that do not. The universe is already filled with structures of staggering intricacy. Galaxies form vast networks shaped by gravity. Weather systems exhibit chaotic dynamics across many scales. Ecosystems coordinate millions of interactions simultaneously. None of these systems show any sign of inner experience. This alone undermines the idea of inevitability. If consciousness were a generic outcome of complexity, it would be far more common. It would appear in many physical contexts, not only in narrow biological niches. Instead, awareness appears tied to very specific constraints. Not just information processing, but integrated information. Not just memory, but memory linked to action. Not just prediction, but prediction grounded in a persistent internal model. Most complex systems lack this combination. They process information locally, not globally. They respond, but they do not unify responses into a single perspective. They evolve, but they do not represent their own evolution. This suggests a different picture. Consciousness is not a destination toward which systems naturally move. It is one possible configuration among many, and it may not even be a stable one. A system can increase in intelligence without increasing in awareness. It can optimize behavior, learn patterns and solve problems without developing any subjective point of view. From a physical perspective, this may often be the more efficient path. Awareness adds overhead. It slows processing. It introduces vulnerability. There is no reason to expect evolution or any other natural process to favor it universally. If consciousness emerges, it does so locally under pressure and for limited durations. It is shaped by contingency rather than destiny. This reframes a common question. The mystery is not why consciousness exists everywhere, it is why it exists anywhere at all. And once inevitability is removed from the picture, the problem becomes sharper, not softer, because now we're forced to confront the possibility that awareness is not written into the fabric of reality, but carved into it briefly by chance and under constraint. Even after stripping away misconceptions, one question remains stubbornly intact. Why does information processing feel like something from the inside? Neuroscience can map neural activity with extraordinary precision. It can track signals, measure correlations, and predict behavior. It can explain how brains integrate information, store memories, and guide action. And yet none of this explains why there is experience at all, why perception is accompanied by sensation, why memory comes with a sense of pastness, why thought is not merely computation but felt. This gap is often called the hard problem of consciousness. It is tempting to treat it as evidence that science has reached a dead end, or worse, that consciousness lies outside physical explanation altogether. Neither conclusion is justified. The hard problem does not arise because physics is wrong. It arises because our descriptions may be incomplete. Throughout history, similar gaps have appeared whenever science encountered a new domain. Heat once seemed irreducible until it was understood as molecular motion. Life once seemed inexplicable until chemistry revealed how complexity could self-organize. In each case, experience lagged behind explanation. The same may be true here. Subjective experience may not be an extra ingredient added to physical processes. It may be what certain physical processes are like when viewed from within. This idea does not solve the problem, but it reframes it. Instead of asking how experience is injected into matter, the question becomes, what kinds of physical systems have an inside at all? This shifts attention back to structure. Only systems that integrate information globally, maintain internal models, and preserve identity over time could plausibly generate a unified point of view. Fragmented processes would produce fragmented or non-existent experience. This does not tell us why experience exists, but it tells us where to look, not beyond physics but deeper into it at the level where information, causation, and time intersect. The hard problem remains unsolved, but it is not an argument for abandoning explanation. It is a reminder that explanation sometimes advances by changing the questions we're willing to ask. And once the problem is reframed in this way, a new line of inquiry opens. If experience depends on how information is integrated, then consciousness may admit degrees not a switch, but a spectrum. If consciousness is not an all-or-nothing property, then it cannot be treated like a switch. It must be something that comes in degrees. This idea changes how the problem is approached. Instead of asking whether a system is conscious, the more productive question becomes how much information it integrates, and how tightly that information is bound together into a unified process. Most physical systems process information locally. A molecule responds to nearby forces, a star reacts to pressure and gravity, a weather system propagates changes through turbulence. Information flows, but it fragments. Different parts influence one another, yet no single state summarizes the whole. There is no global perspective, only interactions. Conscious systems appear to operate differently. Information is not merely processed, it is integrated. Signals from vision, memory, emotion, and expectation converge. They influence one another simultaneously, not sequentially. The system's current state depends on many past states at once, bound together into a coherent whole. This integration is what allows a system to have a point of view, not because it contains a special ingredient, but because its internal structure makes it impossible to decompose into independent parts without losing essential information. Break a crystal and its properties remain predictable. Break a brain, and the organization that sustained awareness collapses. This sensitivity to structure is a defining feature. It suggests that consciousness tracks patterns of causal interdependence rather than specific materials. What matters is not where information is stored, but how deeply different components depend on one another to function. This perspective also explains why awareness resists simple localization. There is no single center of consciousness in the brain, no privileged neuron or region where experience resides. Instead, awareness appears to arise from distributed interactions, from the way many processes constrain and inform one another in real time. Seen this way, consciousness becomes less mysterious but more demanding. It requires systems that are highly integrated but not rigid, highly interactive but not chaotic, capable of maintaining identity while constantly updating their internal state. Very few physical systems meet these requirements. And even among those that do, integration can wax and wane. During deep sleep anesthesia or trauma, integration breaks down. Information fragments. Experience fades not because matter disappears but because structure dissolves. This suggests that consciousness is not something a system either has or lacks. It is something a system sustains, and sustaining it requires continuous work, energy, stability, and precise organization. Understanding consciousness then may ultimately be about understanding which forms of information can bind themselves together strongly enough to create an inside. And that insight leads directly to the next question. If consciousness depends on integration, what role does time play in holding that integration together? Consciousness does not exist in an instant. It unfolds. Every experience depends on what came before it, on memory, context, and expectation. A single snapshot of neural activity frozen in time would not be awareness. It would be structure without continuity. This immediately links consciousness to time, not just time as a clock ticking forward, but time with a direction, a distinction between past, present, and future. Memory anchors the past. Perception occupies the present. Prediction reaches toward the future. Together they form what we call the self, but this structure only works if time itself is asymmetric. If the laws governing experience ran equally well, backward memory would not accumulate, learning would not stabilize, and identity would dissolve into noise. This is where entropy re-enters the story. The arrow of time, the tendency for entropy to increase, allows information to be stored irreversibly. Memories persist because they are written into physical systems in ways that cannot easily be undone. Each act of remembering leaves a thermodynamic trace. Erase entropy's arrow and memory collapses. Erase memory and consciousness fragments. This dependence explains why awareness is inseparable from duration. Consciousness is not something that happens at a moment. It is something that connects moments. The self is not a static entity. It is a process extended through time. This also explains why altered states affect experience so profoundly. During deep sleep or anesthesia, time integration breaks down. Neural activity continues, but memory formation halts. Experience does not vanish because matter disappears, but because temporal coherence is lost. Trauma, neurodegeneration, and certain disorders produce similar effects. The physical substrate remains, but the continuity that binds moments together weakens. Awareness narrows, identity fractures. Seen this way, consciousness is not just information integration in space. It is information integration through time, and time itself is not guaranteed. As we saw earlier, the arrow of time depends on low entropy conditions. It is a feature of a universe that began in an extraordinarily ordered state. Without that asymmetry, neither memory nor awareness could arise. This creates a remarkable dependency. Consciousness depends on time. Time depends on entropy. Entropy depends on cosmic history. Awareness is not merely a biological phenomenon. It is a cosmological one. And that realization forces a sobering conclusion. If the arrow of time is temporary, if the universe drifts toward equilibrium, then the conditions that allow consciousness are temporary as well. Awareness exists only while the universe permits time to flow in a usable direction, and that window may be far narrower than we assume. If consciousness depends on time, memory, and finely balanced information flow, then its rarity is no longer surprising. Silence becomes the default. For billions of years after the universe cooled enough to form atoms, there was no chemistry capable of sustaining complexity. Even after the first stars ignited, most environments were violent, unstable, and short-lived. Radiation was intense. Heavy elements were scarce. Planets, if they existed at all, were inhospitable. The universe was active but not conducive, As structure-accumulated conditions slowly improved, metals enriched interstellar space, planetary systems stabilized, energy sources became more predictable. But even then, the vast majority of environments remained unsuitable for long-term informational organization. Awareness requires more than activity. It requires time without interruption. Biological evolution does not move quickly. It explores possibilities through trial and error, often discarding complexity rather than building it. Most evolutionary paths lead to local optima solutions that work well enough without ever approaching consciousness. This makes awareness not just rare but delayed. Even on Earth, life existed for billions of years without reflective experience. Nervous systems emerged slowly. Integration across time and space took countless iterations. And even then, awareness remained fragile, easily disrupted by changes in environment or energy availability. On a cosmic scale, this suggests something counterintuitive. The universe may not be quiet because it lacks life. It may be quiet because awareness is difficult to sustain. Most systems never cross the threshold where information binds tightly enough long enough to generate an internal point of view, and even those that do may exist only briefly before conditions shift again. Silence in this context is not absence. It is attrition. Countless processes begin, very few persist. Fewer still stabilize into something capable of reflection. This reframes a familiar puzzle. Instead of asking why we do not observe minds everywhere, the more appropriate question becomes why we observe any at all. The universe does not suppress awareness. It simply does not favor it. And when awareness finally appears, it does so late locally, and under conditions that may never repeat. That realization prepares us for the next step. If consciousness is this constrained, then we must ask whether our own existence is typical or exceptional. Once the constraints on consciousness are made explicit, a troubling question emerges. Are we representative of what the universe commonly produces, or are we statistical outliers occupying an unusually narrow path through cosmic possibility? This question matters because many assumptions in cosmology quietly rely on typicality. The idea that our location, conditions, and history are not special. This principle has guided astronomy for centuries, pushing us away from placing Earth or humanity at the center of the universe. But typicality is not guaranteed. It is a hypothesis, not a law. When it comes to consciousness, the evidence is sparse. We have a sample size of one planet, one biosphere, one known lineage that crossed the threshold into reflective awareness. From this alone, two interpretations are possible. One suggests abundance. Perhaps consciousness is common wherever conditions permit it. Perhaps many civilizations arise, think, and disappear without ever intersecting. If so, our existence would be unremarkable one instance among many. The other suggests rarity. Perhaps the convergence of conditions required for sustained awareness is so narrow that it almost never occurs. Perhaps intelligence appears often, but consciousness rarely stabilizes. Perhaps most trajectories through evolution bypass reflection entirely. Physics does not yet favor either view. What it does tell us is this: the space of possible histories is vast, and only a tiny fraction of those histories pass through regions compatible with long-lived integrated awareness. This undermines a subtle but persistent bias. We tend to assume that because something happened once, it was likely to happen again. But in large possibility, space's rare events still occur without becoming typical. A universe can produce consciousness without being a universe that commonly produces it. This distinction is easy to miss and dangerous to ignore. If we are typical, then awareness may be a recurring feature of cosmic evolution, limited but widespread. If we are rare, then consciousness is not a trend but an anomaly. Both possibilities carry consequences, but neither grants us centrality. In one case, we are one instance among many. In the other, we are a statistical accident. Neither position elevates humanity to cosmic importance. What they share is a deeper insight. The universe does not optimize for observers. It tolerates them briefly when conditions allow, and that tolerance may say more about the fragility of awareness than about its destiny. If consciousness is not inevitable, then its future is uncertain. But if it is a physical phenomenon dependent on information energy flow and integration, then one possibility cannot be ignored. It may appear again in forms very different from biology. Artificial systems already process information at scales and speeds no brain can match. They store vast memories, learn from data, and adapt behavior through feedback. From the outside, their performance increasingly resembles intelligence. Yet resemblance is not equivalence. The question is not whether machines can act intelligently. They already do. The question is whether they can ever sustain the kind of integrated, temporally extended structure that gives rise to experience. From a physical standpoint, this is not impossible, but it is not guaranteed either. Artificial systems are optimized for efficiency, modularity, and fault tolerance. Their components are designed to be separable, replaceable, and isolated. This architecture excels at computation, but it works against deep integration. Biological brains evolve differently. They are messy, redundant, densely interconnected. Their components influence one another continuously, often in ways that are difficult to isolate. This lack of clean modularity may be precisely what allows experience to unify. If consciousness depends on irreducible integration, then building systems that avoid such entanglement may suppress awareness rather than encourage it. There is also the question of time. Biological consciousness unfolds within a continuous temporal stream. Memory, anticipation, and identity are bound together by uninterrupted duration. Artificial systems, by contrast, can be paused, copied, reset, or accelerated without internal continuity. From a functional perspective, this is an advantage. From an experiential perspective, it may be disqualifying. None of this rules out artificial consciousness, but it undermines a common assumption that increasing intelligence automatically brings awareness with it. It may be possible to build systems that surpass human cognition while remaining entirely mindless, more capable, more efficient, and yet without any internal point of view. If that happens, it would confirm a central theme of this series. Consciousness is not the destination of intelligence. It is a side path, narrow, costly, and easy to bypass. The next transition in cosmic awareness, if it occurs at all, may not look like an extension of ourselves. It may look like something far more alien, or it may not occur again. Either outcome would be consistent with the physics we have explored. The universe does not contain meaning. It contains matter, energy, space, and time. It follows laws. It evolves according to constraints. Meaning does not appear in any equation. This is not a philosophical claim. It is a physical one. Meaning requires reference. Reference requires memory. Memory requires systems capable of preserving information across time. Without such systems, events simply happen. They do not mean anything to anyone. Stars explode, galaxies collide, entropy increases. None of this carries significance on its own. Meaning enters the picture only when a system exists that can assign value, when information is not merely processed, but interpreted relative to goals, expectations, or internal states. This is why meaning and consciousness are inseparable. A system without awareness can respond to signals. A system with awareness can care about them. Care is not emotion, it is prioritization. It is the act of distinguishing between what matters and what does not, based on internal models that persist through time. From a physical perspective, this makes meaning an emergent phenomenon. It does not reside in objects. It does not exist independently in the universe. It arises when certain informational structures reach sufficient depth and integration. This has a subtle implication. If consciousness is rare, then meaning is rare as well. The vast majority of the universe is not meaningless in a tragic sense. It is meaningless in a literal one. There is no internal perspective from which events could acquire significance. Meaning is not missing. It is absent because the conditions required for it almost never occur. This reframes how we think about purpose. The universe does not supply it. Evolution does not guarantee it. Physics does not encode it. Meaning appears only where awareness appears and disappears when awareness collapses. This does not diminish its importance. It makes it fragile. And fragility is a recurring theme. If consciousness is temporary, then meaning is temporary too. Both exist only within a narrow window carved out of entropy's rise. The universe does not preserve meaning. Systems do, and that realization prepares us for the next step. If meaning is emergent and fragile, then awareness itself may occupy only a brief phase in cosmic history. If meaning depends on consciousness, and consciousness depends on precise physical conditions, then one conclusion follows naturally. Awareness is not a permanent feature of the universe. It is a phase. Like stars, galaxies, and habitable planets, consciousness exists only while certain conditions hold. When those conditions change, it fades not dramatically but quietly as structure dissolves and integration breaks down. This fragility is not hypothetical. On small scales, we see it constantly. Consciousness narrows during illness, injury, and exhaustion. It fragments under stress. It disappears during deep anesthesia or coma. The physical substrate remains, but the delicate balance required for integrated experience does not. On larger scales, the same principle applies. Consciousness requires stable energy gradients, long-lived structures and environments that change slowly enough for memory and prediction to remain meaningful. These conditions are not eternal. Stars exhaust their fuel, planets lose atmospheres, galaxies drift apart as expansion accelerates. Over cosmic time, the universe becomes less hospitable to complexity, not more. Entropy does not destroy awareness directly. It erodes the conditions that allow awareness to persist. As energy gradients flatten and structure decays, the informational regimes that sustain consciousness become harder to maintain. Integration fails first. Memory fades next. Experience disappears last. This suggests that awareness occupies a narrow temporal window, opening long after the universe begins behaving predictably, and closing long before it reaches equilibrium. We exist near the center of that window not because it was designed for us, but because only here can observers exist at all. This realization carries no drama. It simply places consciousness where it belongs among other transient phenomena that emerge, persist briefly, and vanish without leaving permanent traces. The universe does not remember its observers, and this leads to an uncomfortable symmetry. Just as consciousness was unnecessary for the universe to function before it appeared, it will be unnecessary after it is gone. The cosmos neither anticipates awareness nor mourns its absence. It allows it for a time. The universe does not notice consciousness. This is not a statement of insignificance. It is a statement of scale and causation. Stars do not burn differently because they are observed. Galaxies do not form structures in response to awareness. The expansion of space does not slow because something is watching. Physical processes unfold exactly as they would if no minds existed at all. This indifference is often misunderstood. It is not hostility. It is not dismissal. It is simply the absence of feedback. The universe does not react to observers because observers do not alter the laws that govern it. Consciousness does not add a new force. Meaning does not bend spacetime. Experience leaves no imprint on the equations that shape cosmic evolution. And yet this indifference does not render awareness irrelevant. Relevance is local. Within a conscious system, experience matters profoundly. Decisions influence outcomes. Values shape behavior. Memory guides action. Meaning organizes internal states and future possibilities. But none of this propagates outward into the universe at large. This asymmetry is crucial. The universe enables consciousness by permitting certain conditions. Consciousness does not enable the universe in return. The relationship is one way. This clarifies a common confusion. To say the universe does not notice us is not to say that consciousness is pointless. It is to say that meaning is not a property of reality as a whole, but of particular configurations within it. Meaning exists in systems not for the universe, and that distinction prevents two errors at once. It avoids cosmic narcissism, the idea that awareness must be central, And it avoids nihilism, the idea that indifference negates significance. Significance does not require recognition by the cosmos. It requires coherence within a system capable of valuing. The universe does not care that it is understood, but understanding still occurs. And that occurrence is not trivial. It is rare, it is temporary, and it is local. Which brings the story to its final step. If the universe does not notice us and consciousness is fragile, then the value of awareness cannot come from outside. It must come from within the process itself. The universe did not set out to understand itself. For most of its history, it did not. It expanded, cooled, and evolved without awareness. Structure formed, entropy increased. Time flowed forward indifferent to observation, and then very late and only in narrow regions something changed. Matter arranged itself into systems capable of memory. Information bound itself across time. A point of view appeared. Not because the universe demanded it, not because physics required it, but because under rare conditions awareness became possible. This did not transform the cosmos. Galaxies continued to drift apart. Stars continued to burn and fade. The long trajectory toward equilibrium remained unchanged. What changed was local. For a brief moment in cosmic history, the universe contained regions where it could be experienced, where events were not just happening but being registered, where time was not just passing but remembered, where patterns were not just forming but understood. This does not grant consciousness cosmic privilege. It grants it context. Awareness is not the goal of the universe. It is one of its most delicate byproducts. A temporary phase sustained only while energy flow structure persists and time retains a usable direction. When those conditions fade, consciousness will fade with them. The universe will continue unchanged. But for now, something unusual is happening. In one small corner of a vast indifferent cosmos, matter has become organized enough to ask where awareness comes from, and whether it could ever have been otherwise. If the universe has no beginning, then consciousness is not its culmination. If the universe does have a beginning, consciousness is not its reason. Either way, awareness does not complete the universe. It briefly illuminates it, and that illumination does not require permanence to matter. It only requires that for a short span of time, the universe was capable of being known from the inside.